Hi, my name is Talia. I'm a high school senior and I love teaching others about chemistry. This YouTube channel is a supplemental resource for anyone who may be needing some help in their chemistry classes. This week, I'm going to be finishing up my series on gas laws and talking about Avogadro's law as well as the ideal gas law. So if you need help with either of those topics, feel free to keep on watching. And without further ado, let's get started. Okay, so today I'm first going to be talking about Avogadro's law, which just says that at a standard temperature and pressure, 1 mole of any gas will occupy 22.4 liters of volume. And standard temperature and pressure are abbreviated as STP. So the really important thing with this law is that you make sure to only use this conversion of 1 mole that equals 22.4 liters when the problem explicitly says that the conditions are STP. Otherwise, your conversion is wrong because this law only applies to specific conditions, which is 0 degrees Celsius and 1 atmosphere. So let's do some example problems. So if we want to find the volume of 0.400 moles of a gas at STP, my first light bulb going off is that we have STP. So I don't need to do like any other equations. I can just do 0.400 moles and then write a regular conversion that 22.4 liters is equal to 1 mole. And my units of mole cancel out. And then all you have to do is plug into your calculator 0.400 and then multiply it by 22.4. And we're going to get 8.96 liters as our volume. Next, this is kind of a multi-step problem, but nonetheless, it is still using everything we've learned before. So we are trying to find the mass of 400 liters of neon at STP and how many atoms of neon are present. Okay, so we are going to first convert our liters to moles because that is what we do with our STP conversion. So we have 400 liters times 1 mole over 22.4 liters. So if I divide 400 by 22.4, I get 17.9 moles neon. And then you want to keep your unrounded version in your calculator. And then I'm going to do 17.9 moles neon and multiply by molar mass. So we have 20.18 grams per mole. And that is going to get me 360 grams of neon. So that is the answer to our first question, and actually not be very smart to just go straight to mass because we need our moles for the next part of the question. So I'm now going to answer the next part by writing that 17.9 moles of neon. And then we know that to get from moles to any kind of particles, if you remember from previous videos, we need to use Avogadro's number. So I'm going to write that 6.02 times 10 to the 23rd atoms equals 1 mole. And remember, I found moles in my first conversion. So then I'm going to still use my unrounded number and multiply by 6.02 times 10 to the 23rd. And then I'm going to get 1.08 times 10 to the 25th atoms of neon. So that is the answer to our second question, and that is Avogadro's law. Super easy, just like any regular conversion we've learned, but just the key thing is that you notice if the problem says STP or not, because if it doesn't, you cannot use Avogadro's law. Okay, so the next and last gas law we are going to go over is the ideal gas law, which basically combines all of the gas laws, including Avogadro's law and the combined gas law, to relate pressure, volume, temperature, and moles in any kind of condition. So this is not at STP. So the ideal gas law is written as PV equals nRT. P is pressure, V is the volume, N is number of moles, T is temperature, and R is a gas constant, which depends on your units of pressure. So if your units of pressure are in atmospheres, you use this gas constant. And if your units of pressure are in pascals, you use this gas constant. And I forgot to write here, your temperature must be in Kelvin. So now we're going to do a practice. You use the ideal gas law when you are involving moles and pressure and volume and temperature with non-STP conditions. If you are involving moles of a gas at STP, you are going to use Avogadro's law. Non-STP, use the ideal gas law. Just relating pressure and volume and temperature, you're going to use like Boyle's law, Charles's law, Gay-Lussac's law, and the combined gas law. So let's do some examples. So we want to find the mass of 40 liters of helium at 290 Kelvin and 0.860 atmospheres. So to get eventually to mass, I first want to get to moles because then I can multiply by molar mass. So I'm going to set up my ideal gas law equation. And here we have, so if I write it out, we have PV equals nRT. So I'm going to plug in what we know. Our pressure is 0.860 atmospheres. Volume is 40 liters. And I'm trying to find moles so that I can convert to mass. Our gas constant, because our units of pressure are in atmospheres, is going to be 0.0821 liters atmospheres per mole Kelvin. And our temperature is 290 Kelvin. So now what we're going to do is divide both sides. And we are going to divide it by 0.0821 liters atmospheres per mole Kelvin times 290 Kelvin. And remember that when we're dividing by multiple things on the denominator, you are normally, and especially in this case, you're going to want to multiply them together. So you want to put parentheses around your denominator. So our units are now going to cancel. So we have atmospheres cancel out and liters cancel out. And on the denominator, our Kelvin cancel out because 0.0821 is actually written as liters atmospheres over mole Kelvin like this, and we're multiplying it by Kelvin. So Kelvin is going to cancel out, and all we're going to have left is moles. So now I'm going to plug this into my calculator. So I'm going to do 0.860 times 40, and on the denominator in parentheses, I'm going to write 0.0821 times 290. I believe I mentioned this in one of the past gas law videos, but if you were to just do 0.860 times 40 divided by 0.821 and then times 290, your order of operations is going to be messed up. So when I plug that in, I get 1.44 moles of neon. Now we want to convert to mass. So we have 1.44 moles of neon, and this is just like any other conversion with moles and mass we've done in past units. I'm just going to multiply by molar mass. So I have 20.18 grams neon over 1 mole of neon, because that's the molar mass on the top. Moles of neon cancel out. And then I get my final mass as 29.2 grams of neon. Okay, so our next example problem is what is the volume of a sample containing 0.600 moles of nitrogen gas at 400 Kelvin and 1.05 times 10 to the 5th pascals. So I'm going to do the same thing. We are looking for volume this time. So I'm going to write PV equals nRT. And then we have our pressure. We have 1.05 times 10 to the 5th pascals. We are looking for volume, so I'm going to leave that as V. We have 0.600 moles. And our gas constant, this time we are going to use 8314 liters pascals per mole K. And then I'm going to multiply by temperature. We have 400 K. So now we have all of our givens. And so to isolate volume, I'm just going to divide both sides by 1.05 times 10 to the 5th pascals. And our units are going to cancel out. Obviously, this will cancel out. Moles over here with 0.600 is on the numerator, and with the gas constant, it's on the denominator. So moles will cancel out there. Kelvin is the same situation. It's on the numerator with 400 Kelvin. It's on the denominator in the gas constant, and units of pascals will also cancel out. So all we are left with is liters. So now I'm going to plug into my calculator 0.600 times 8314 times 400 divided by 1.05 times 10 to the fifth. And I'm going to get as my volume 19.00 liters. And I'm just going to write N2. So that is practice with the ideal gas law. It's just similar to the other gas laws in the sense that you'll be solving for one of the variables given other information. And there will be times like the first example problem where you need to use that information that you find from the ideal gas law in order to calculate new information. And we'll further that kind of discussion on my next video in gas stoichiometry. So that is the end of this video. I hope you enjoyed this week's video. Next week, I'm going to be talking about gas stoichiometry, which shouldn't be anything too new. I'm just going to combine what we've already learned about stoichiometry and what I discussed in this video about the ideal gas law and possibly some of the other gas laws in order to solve new parts of stoichiometry problems. So I hope that if you need help with gas stoichiometry, you will join me back next week. Feel free to leave any comments or questions in the comments below, and I will do my best to answer them. I hope you enjoyed this week's video, and good luck with learning the rest of your chemistry.